Now, here we have one of our tea bags, and this isn't a tea bag, it's a bag of tea. And we puffed it up like a pillow with air instead of injecting in hot water. And there's a generous dose of sugar in this bag. It's a granulated sugar.
And the Russian sugar is kind of neat because it's fairly coarse grained. It's around 3/4 of a millimeter to 1 millimeter in diameter. And here's a transmitted view again of the pouch puffed up with air. You can see the tea bag floating around.
And so you can shake this bag up just like we saw with the larger Ziploc baggies, and we can look at the fate of the sugar crystals as they undergo collisions with each other. So let's go ahead and see what happens. Here's a close-up showing sugar crystals after they've been stirred up, and this is real time. Look how quickly they assemble themselves into these large agglomerates.
It's amazing what you can see when you're just sitting at or floating at breakfast galley table, getting ready to drink a morning beverage, and all of a sudden some Saturday morning science comes out at you.
Sugar, which is organic, molecular, crystalline solid, it behaves similarly to what we saw with this ionic crystalline solid sodium chloride.
When I first saw this, you can actually see these particles accelerate, deaccelerate with no external disturbance.
We see the sugar crystals moving around due to electrostatic forces. You see a big floccule moving down. It collides with the wall, transfers some charge, and now it's moving in the opposite direction. So electrostatic forces are certainly important in governing the dynamics of what we see here.
And when I first saw this, it almost looked like it was some kind of a fish bowl with little tiny fishes swimming around in it. It kind of reminded me when I was a kid and I mail-ordered from the back of a comic book, I mail-ordered these sea monkeys. And this is actually more interesting to watch than the sea monkeys were.
Again, here's a close-up showing the sugar crystals moving around. They almost look like little creatures swimming in a Petri dish, and they're moving around in electrostatic forces. If you touch the side of the bag, as we demonstrated here, the act of touching the side generates enough static charge to draw the sugar crystals to that spot, as we're seeing here when we're rubbing the side. So it's kind of like the static charge that's generated when you scoot your feet across a rug, and then you touch the sleeping dog on the nose. But in this case, we don't have any sleeping dogs, fortunately. Now here we see the same thing, only this is with a bag of instant coffee.
This shows my dedication to science. This is my last bag of coffee.
And the coffee grains are about 100 microns in diameter, and they're, I guess I'd characterize coffee as a nondescript organic solid. And we can see when we shake up the bag of coffee, it again exhibits the same kind of behavior that we saw with the sugar and the sodium chloride. It rapidly assembles itself into these large agglomerates.
And obviously, going on in here, it's a plastic bag. You got friction at the side when I shake it. There's charge forces involved with these particles.
Now here we have one of our culture flasks filled with water and the titanium dioxide mica flakes that were used for tracer particles.
These are 5-micron diameter mica flakes, and these are the same kind of flakes that are used in the cosmetic industry to put sparkles in things like shampoo and eyeshadow and stuff like that. And fluid dynamicists have discovered that these make great tracer particles for doing experiments, which of course forever changes your view of sparkly eyelids.
And we shake up this flask, and there's no visible structure within the flask.
Now, here is 2 days later. This thing has sat quiescently in the environment here on Space Station for 2 days, and now let's take a peek at it. And again, I'm going to shine a flashlight from the back side. And look at that. Chain agglomerates forming. And these, the first order, look just about the chain, like the chain agglomerates that we saw in the bag of coffee and the bag of tea. But these are 5-micron diameter mica flakes that have somehow moved around inside here and formed these chain agglomerates.
And then as time goes by, as weeks go by, here they are after about 3-4 weeks, you see these large chain agglomerates made up, centimeters on an edge, made up from 5-micron diameter mica flakes. So even in a system with particles as small as 5 microns, with a surrounding density fluid of that of water, we see the same kind of behavior as we did in the sodium chloride, the sugar, and the coffee. So I found this amazing that you could have particle agglomeration events happen so quickly over such a diverse particle composition and size and density of surrounding medium, and all of this behavior appeared to make these large chain agglomerate type clusters that had a fair amount of integrity to them. And I thought this was amazing, and perhaps it might have some relevance in planet formation when you look at dust grains that condense from a solar system nebula and how these dust grains end up being fist-sized rocks where mutual gravitation can eventually build planets. Perhaps it might help elucidate some questions in that arena.
I think we have the answers to many of the questions for the formation of our universe, all seen here in our bag of tea.
And it looks to me like what's happening here. We have electrostatic forces which are bringing these small particles together.
And Houston Alpha, that's it for our Saturday morning science.